Hi, okay. So today I would like to share you something about recent technology on deep learning for photo restoration. So everybody knows like a picture is worth 1,000 words. So actually in our daily life, we have been using our iPhone, using our mobile devices to capture many pictures every day. Pictures have been like one of our prominent mediums for us to communicate with others and share with others. So actually, however, as we know that there are always kind of unhappy things happening when we capture pictures. Here, I will show you some like undesired result when you're taking pictures onto all kind of facts. So one is the so-called a degradation. So the degradation refers to that we actually, when we're taking a picture using our camera, certain information is lost or the quality of the image is not up to your expectations. So for instance, if you look at the left image, it's called image with noise. So you can all see those kind of very random dots showing up. Okay, the right one is called low lighting image. That is when you taking a picture in a low light conditions in the dawn or or at night, because there's no sufficient light in the scenes. When you take a pictures, it looks like dark and you cannot see many details. Another one is called motion blur. So if you today every phone company is talking about, you have very great cameras to taking pictures using a mobile phone. However, because usually when you're using mobile phone to take pictures, you don't bring a tripod. As a result, if you're taking pictures with like a zoom in mode, then you will suffer from the so-called motion blur. That is, when you're taking pictures, your hand or your mobile phone is not like very steady. As a result, the image will blur out. Another one is called low resolution. That is, if you're taking pictures of something very tiny, your camera cannot provide sufficient resolution so that you can see all the details. Okay, so here is, today I'm talking about picture restoration and enhancement. That is, suppose you have a picture which is not so great and did not really like meet your expectation. How you can get a better one from what you have. So here I list some examples. The first one is so-called image denoising. That is how I remove all those like very unpleasant, those dots from these pictures so that it looks clean and good. The second one is called contrast enhancement. So if you have a picture taken in the low light conditions, you want to recover all the details, which means you have to enhance the contrast of the pictures so it looks much vivid with all the details. Third one is deblur. So suppose you're taking pictures which matters to you. However, it is blurred out. Can you recover the good one with all the sharp details? The last one is called super resolution. Basically, you have a picture which the resolution is low so that you can't recognize important details, like the code of this circuit. Then can you boost the resolution by the software so that you can see all the details. All right, these are some representative applications in real life about picture restoration. This is another one. For instance, in Singapore, we often rain a lot. Suppose you are taking a picture from indoor, and you can see that often, if the rain is heavy, there are many raindrops on the windows. Or if you are driving, like you have a raindrops on the windshield. If you're taking picture from indoor, how you can remove those raindrops so that it looks like you are taking this picture in a sunshine day. But the real picture is actually taken in a heavily raining day from indoor. How you do that? All right, so let's start a basic introduction about images. So image usually is captured by some cameras, which you have some light source passing through to the object. We call this scene element. Then it will bouncing this light into the camera or into your mobile phone. Then the lens will capture this information and form an image. All right, eventually, but today everybody is using the so-called digitalized image. So what is a digitalized image? Let's think about an old-fashioned image, a grayscale image, no color. Then it's actually an array of numbers. I can show you, here I only show you a small portion of the image of some paper. And you can see they just array from horizontally and vertically, an array of numbers. And in mathematics, it is called matrix. Okay, so what is a color image? And color image is actually three gray image, but these they are representing three different color channels, RGB, red, green, and blue. These three prime color. So here I show you one color image. This image is actually composed by three like grayscale images. One represents color in red, one represents color in green, and the red one represents color in blue. Okay, it's just array of numbers. That's what I try to say. Of course, here I show you how the image manipulation actually can be corresponding to our mathematical, like basic mathematical basic operations. For instance, here I show you one image from astronomy. Then you can represent by array of numbers. Here I only show you 4 numbers. Then you plus 64, which you plus a constant, the image looks a little bit brighter, right? If you minus a constant, the image looks a little bit darker. That's what addition and subtraction by a constant is doing if you look at the, in terms of image manipulation. Similarly, if I want to synthesize some image which looks like you are taking in the raining day, I take a picture, then of course I have to have, I need an umbrella to make it realistic. Then I add some rain streaks. I sum them together. You can see it looks like an image taken in a raining day, right? That's the matrix additions. It can produce very sophisticated effect just by this matrix, simple matrix arithmetic. All right. Okay, but we are doing different things. We are not saying how we're going to synthesize an image which appears to be realistic from from something simple. Here we try to say if we give you something bad, how you can get something good out of it. That's actually what people call this inverse problem, because you want to reverse the process which you don't want to. So for instance, here I look at a noisy image which is, you can see it contains all these undesired random dots. It actually can be modeled by the addition of 2 things. One is the clean image without noise. Another one is noisy. For instance, you have this array of numbers equal to array of numbers plus another array of numbers. So what image denoising do is, I only have the left one. I don't know the right one. How can I guess what is the clean image so that I get an image with better quality? Next, and this one is a bit harder to explain. That is called image deblurring. Image deblurring, I should introduce a basic concept called convolution. What convolution does is that you take for each, suppose I have images, right? I have so-called pixels. Pixel is the 1 unit of an image. Then you take an average of all the neighboring values together. Then you produce the output. So the effect of such operation is that it will blur out the content of an image. See, mathematically, we call this a convolution. And you have the left a matrix, convoluted a small matrix. This small matrix in image processing, we call this convolution kernel or the blur kernel. That is, it describes how you can average out all these local pixels to produce a blurred one. All right. Essentially, if this animation show you that I just take nine pixels and I average them out using the weight given by this 0, 1, 2, 2, 2, 0, and 0, 1, 2. That is how the image blurring is doing. As a result, I start to can, sorry, something, okay, never mind. So I have essentially, okay, they have issues here. I have a blurred image is actually equals to a sharp image convoluted with so-called blur kernels. Of course, here we have minor issues of the sharp image. You just think about it as a sharp image, a sharp one of this paper image. Okay, then what this non-blind deblurring doing is that I don't know what image is, and I don't know what noise is. Another is called blind deblurring is that I try to recover a blurred image without knowing how it is blurred out, which means I have Y, but I have something unknown, convoluted with something unknown, plus something unknown. That is so-called image deblurring. So here I will write a simple mathematics. Please just bear with me. So all these problems can be described by so-called linear functions. Here I write in an abstract way. That is, you have Y equals to AX plus N. This A is just people saying it's how it is, how the image is degraded. And Y is what we are given. X is what we want. And N is noise. So it's Y equal to AX plus N. And you have a different degradations which actually corresponding to different degradation matrix. For instance, if denoising, A is identity matrix. If blurring, it's convolutions. So eventually, all these problems can be described saying how I can solve these linear equations. And I think you have learned a lot about how to solve linear equations since secondary schools. But here, again, they are same problem, but they have different properties. Okay, hold on, sorry. Let's jump a bit faster. The problem is that this problem indeed is a very hard problem than you encountered in your high school or even in your college. That is, you have more unknowns than equations. So that is, suppose you have one image, which is 3,000 times 3,000 pixels, which end up with 9 million unknowns. Try to guess. But you're only given, for instance, you only have maybe 1 million equations. So 1 million equations, 9 million unknowns, which means it's heavily underdetermined, which means you have to guess from many possible solutions. That's the hard part about so-called inverse problems, which actually is what we often say the photo restoration problem. So in last few years, right, deep learning has been one like very hot name in everywhere, from science, from engineering, also in our daily lives. So deep learning is a one-man tool in our AI for doing all the fancy things which we cannot expect to be able to do before. Same things for these photo restorations, and actually this deep learning also have been prominent tools, which so that we can go beyond our physical limitations to get high quality images. For instance, for instance, yesterday I watched the announcement of Apple. They're talking about machine learning in their chips, and they're all doing so-called, probably heard a name so-called computational photography. Actually, today, this computational photography is trying to using all the algorithms to give you a better quality images using machine learning techniques. That is actually using deep learning techniques. So today, I will hope that I can show you that how deep learning can be used to improve the capturing of images for our personal entertainment as well as for the industry. All right, so here I show you one diagram that suppose I have a noisy image as input, I passing through a neural network, which will give you a good one. So why image processing and this image restoration is closely related to deep learning is actually, it's not surprising. For instance, in our human intelligence, vision is actually one of our main part of our intelligence. If we understand actually most of our 70% of neurons in our brain belong to our vision system. That is 70% of our brain is devoted to processing the information seen from our eyes. That's the main part. So deep learning is actually has some analog to this our brains. Is actually deep learning is actually built up a neural network so that it can simulate what's happening in our brains. All right. So here, the basic structure is the same. A neuron means it will receive a few inputs. Then you're going to have an activation functions to see based on the input. For instance, if the input is positive, let's through. If the input is negative, cut it out. That's the basic mechanism in neurons. All right. Continue. Deep neural net often is called deep neural network, DNN. Deep neural network means it's a network with many layers. Okay. So we have two terminologies for that. One is so-called depth. That is how many layers in the network. And another is called width. Width means it's a vertical. It's a number of neurons or number of nodes along the vertical direction of each layer. So you have width and depth. So a deep neural network means, or the deep learning, so network used in deep learning is that the depth is very large. You have many number of layers. Well, so here I would like to show you that actually it looks like a mystery to might look like a mystery to you, but it's actually very simple math, just like what we learned in high school. Let's give you examples about a single layer network with only single node. Then you have many inputs, x1 to xn. Everyone is assigned a weight. Then you sum them together. You get a value, right? So suppose this value is positive, let it pass through. Suppose the value is negative, just set to zeros. That's it's already a single layer neural network, which means mathematically you just take a summation of input with the weights, then you let through or cut it out. It's actually very simple nonlinear functions. Let's continue. Suppose I have 3 layers. What is 3 layers? Because you have a many nodes, right? These many are sum them together. So which means you sum the previous one, but with different weights. It's called summation. So in other words, many nodes on one layer refers to some summation of many simple functions. So what a deep network is that you have many layers, right? Which means you have a functions which is constructed by the composite rules, or called variable substitutions. I think you have seen this before as well. That is, you compensate the function again and again to change them, make a chain. That's what DNN is in mathematics. Still very actually it just can be accurately described by mathematics. Well, so once you have a network, let's start so-called introducing the learning. Learning is many types of learning. I start with so-called supervised learning. That is, I know what I expected from the input. I know what the prediction should be on certain data. This is called training data. So what learning is doing is that he just adjusts the parameters I just described here. In my, here you already see the weights like W0, W1, all the way to Wn. I just adjust this weight so that on the data I have, I can accurately predict what the output. That means I can produce the prediction which roughly is the same as the truth contained in the training data. Then after I train this model, which essentially means I determine all those parameters, then I can use it to do all the jobs. People call this testing. That is, I use this model, which is trained with this training data. I try to run on the unseen data, new data, and hopefully it can do as well as it did for training data. That's supervised learning. So here I give you one simple example called supervised deep learning. That is, I have two classes of images, right? All are the image of pets. One is dog. I'm using so-called 1 to represent it. The other one is called cat. I use -1 to represent it. So my job is, suppose the network is fed with many such images, two classes, cat and dog. Then I turn up my parameters of the network so that it can accurately predict this cat and the dog. Okay, so mathematically it means you are making correct one means you have the same values, right? Suppose it's a dog, it should be 1, which means mathematically you are somehow adjust the parameters so that the error on the prediction is as small as you can, which can write it as a like minimization problem. So you are done. This is training. Okay, so similarly, suppose now we are doing so-called photo restorations. Of course, we still have a training data set. That is, I have a bad image, yi, and I want to get good image, xi. Suppose I already have some very high quality cameras do this job. Then I can collect all these data. So I just have a network. So I take an input as this bad image and output good image. All right, then it looks like you are done, right? Just use it as a black box. However, that's not true. Why it is not true is that so we have the so-called overfitting problems. That is, usually a deep neural network will have millions of unknowns. And we don't have millions of the images to train a network. So overfitting means it might doing well on the training data, but it will do poorly on testing data. So here, but if you look at the classification I'm talking about, you want to classify a pet image into a cat or a dog, you want to identify it. Then you can, it mathematically means you have images, which might be 1,000 times 1,000 times 3, map them into labels, which can be either 1 or -1. However, for the image restoration, you cannot do that. Why? Because the input is the image. The output is also image, which means you try to learn a mapping or learn a function which map 3 million numbers into another 3 million numbers. I mean, no way you can do that successfully. All right. So in other words, here you need specific techniques to use deep learning for image restoration. That is different from classification or recognition, other AI job. Why? So today I will talk about two things. I show you that how mathematics and statistics can help to do this AI for photo restoration. That is, if you want to do the deep learning for the photo restoration, you need to combine math, statistics, and machine learning together so that you can have a good solution. Here I show you two case studies, okay? The first is, if we look at the problem, actually, there is a long history that we developed so-called mathematical method into some like optimization formulations. That is, I want to solve this underdetermined linear systems with many equations, but with more unknowns. I just say I want to minimize this A so that the equation will be nearly satisfied and you have certain prior is applied on the image. This prior is the property of image you want to have. So traditionally, that's how the mathematics is doing. As a result, because suppose I assume you have basic knowledge on optimization, that is, it's difficult to solve. You don't have explicit solutions. You have to run some iterative numerical solver to solve it. So iterative solver means you iteratively refine your solutions. Suppose you have y, you make first guess x1. Based on x1, you get second guess x2, so on and so on. Eventually, you get, after many iterations, you get more and more refined. Then the solution will close to what we want to have. That's called iterative method. Well, that's it. As I mentioned that if you're directly using a deep neural network as a black box to learn the mapping between the bad image and the good image, you will fail, or the performance will be not so good. However, a better approach, which is to combine this optimization and deep learning, that is, you still follow the traditional method for photo restoration. That is, you have some optimization formulations, then you gradually refine your estimate one by one. So x0 to x1 to x2 and so on. Then eventually, you hopefully get something good. But how deep learning can help here is that if you look at the first equations, we don't know phi well because it's the physical properties of the image. Deep learning here can help us to learn these physical properties. That's it. So basically is that we're still doing this step-by-step refinement using some iterative method. However, how to iterate, how to refine it in each step, I use a deep neural network to learn how to do this step-by-step refinement. That is so-called optimization unrolling. It actually also people call this a deep neural network, which can be interpreted in terms of mathematics. So here I show you some results we developed recently. 4 examples. The first is the called noise-blind image. Sorry, not deblurring, but deblurring, yes. Basically, you have a noisy, blurred photo with as input. So you can see that from the left, it's like very blurred out. You might still can recognize it's butterfly, but all the details are gone. And also, you have very unpleasant random dots. Then, using these so-called optimization unrolling-based techniques, you can actually deblur the result and suppress the noise at the same time. So here you can show the right is the output from a so-called VM-based deep learning for the image restoration. That is, you combine the mathematical method together with this deep learning, you can produce amazing result. That is, you get a better one, which is blurred, don't worry. You can get clear one. The second is called image enhancement in night light conditions. Of course, today, if you have a very good iPhone mobile device, maybe you can have so-called the night mode for you to capture images. But in the case that your picture taken in night mode is not successful, or you don't have very fancy device to do job well, can you recover it? I said yes. Again, we still based on the so-called retina decomposition model. Together with this deep learning, you actually can enhance as a post process, just like you do things in Photoshop. You can just take this image which looks poor with little contrast. You don't see all details. You can boost its details to see that to have a better result. So clearly you can see the right image actually has much vivid color and much pleasant details to present. Last one, about text images. So often today, especially, I think everybody often using your phone or something to take picture to scan the document. In older time, maybe you are using a scanner, but today everybody just using your phone, all right, to scan the document and send it out as a soft copy. But it happens that sometimes happens that you might have a low resolution and blurred the document, which will be disaster if you send them out. Why? Because if you look at the left image, you actually cannot see. I don't think you can recognize any letters on it. So you don't know what I'm talking about. However, combine this deep learning and optimization unrolling will allow you to recover this low resolution blurred document image into a good one. Of course, here indeed, what I did is that the left is actually a technical report on some technical content, some mathematics, okay? So you can see that the recovered image from the deep network indeed can show you all the details and readable. All right, so that's the power that you combine mathematical method and deep learning to produce very powerful software so that you can post-process the bad images and convert them into good ones. Well, next. So next is another category. It's called unsupervised learning. That is, of course, you say, I have a network. I want to collect all the training examples to train the network. That is, I adjust the parameters to get, so let the network learn how to process the image. All right. However, collecting training examples can be very expensive and sometimes very challenging. For instance, if you want to train a good, if you want to build up a good, let's show you one example. If you want to do well on this one, you have to collect probably, we build up a data set with probably 100K images so that it provides sufficient training examples for us to train the network, which will be very time consuming as well as it can be expensive. All right, so another issue is that for many scenarios, you cannot collect many training examples. If you go to hospital, right, then you will take medical examination or diagnosis. The doctor will ask you to go to a CT scanner or some MRI. That kind of data you cannot collect them. Why? Because of the privacy issues. So in other words, if you go to specific domain, collecting training data can be challenging and expensive and sometimes impossible. So here is a setting, how we can do so-called unsupervised learning. That is without training examples. That is, but it looks strange in the beginning. That is, if you have a deep neural network, I don't show you how it is solved, the problem, then how the machine itself know how to solve the problem. Just like you have a robot. You don't teach a robot to expose him some what he's expected to do. How we know what he should do? So that's a challenging part about unsupervised deep learning. Well, here is a bit part because unsupervised deep learning is a bit more challenging that you require some advanced knowledge in statistics. Here I will go very briefly about statistics, especially the Bayesian inference. If you feel it's too overwhelming, you can just omit it. So basically about Bayesian inference is that I have some data comes in. Bayesian inference is that can I get some probability understanding about this data? So in statistics, it's called probability distributions. That is, if I give a data, how I know is probability distributions. That's called Bayesian inference. This is based on so-called Bayes theorems. That is, you have so-called conditional probability. Give a B, I know the probability, what's the probability of A, which actually can be expressed as given the probability, given the event of A, what's the probability of B? Multiply the probability of B divided by the probability of B. Okay, sorry. It's equal to probability of given event A, the conditional probability of B, multiply the probability of A divided by probability B. This is a very famous theorem called Bayes theorem. I will not go to details. So actually this Bayes inference is that, the idea is that give me the data, how I can guess the probability functions of it. Of course, you cannot, because theoretical probability functions can be arbitrary, right? So what people usually did is that I assume what is the probability function is, but I don't know its parameters. That's how it is. That is, give me data, how I can guess what is the parameters of the probability function. Well, this is more technical, but this is very basic in the statics. That is, suppose I have image, nothing else, which means I cannot get to the truth, right? What I have is that, can I have a result which is most likely, or it is best among all the possibles in the average sense? This is called conditional expected values in statics. That is the average optimal estimation over all the possible blurred images, okay? Then I can rewrite this in terms of mathematical formulas. This is so-called Bayesian inference. Essentially, the optimal estimation will be an image with integration of a function h, which is the functions which is the parameters with phi. Phi is used about how to determine it to get the truth. Then I have the post probabilities. This one is difficult to do in traditional Bayes inference. It requires a knowledge about the truth. But what happens if we don't have it? The idea is that I can, using a network, which is so-called Bayesian network. That is, my weight is different from the one I described in 10 slides before. That is, every weight now is a random variable, like Gaussian functions. So remember, we know what's the Gaussian function, right? A Gaussian variables means it follows a normal distribution, and you have two parameters to determine. One is its expectation, that is the center, and its variance or standard deviation, sigma. Sigma measuring like uncertainty of this variable. And then I have a network. This network, every weight is Gaussian random variables. You combine together, you produce a very complex probability functions, and hope that these probability functions is correct model when you describe the data. Okay, so that's it. Based on this Bayes inference, we actually can, using network, to approximate the posterior probabilities, which actually give you a formulation. That is how you're gonna estimate the parameters of each Gaussian of the weight of the network, so that you can train a network. So you can see here that is, we don't have any additional source to train. You have the Y, single Y, nothing else. That is unsupervised, or called self-supervised. That's it. That's the idea. That is how to using classic statics to help deep learning, so that you can using the so-called self-supervised deep learning for image denoising. Here I give you one example, the denoising. Okay, that is, you have input, right? Nothing else. You don't expose this any other noise image to the network. You still can learn itself by predicting a probability distribution functions. Then you take average, you get what you want. Another one. The same one can be done using, the same idea can be used to deblur the image. Here I give you one result. Okay, here I mentioned most are just about images, but be remember that here I only show you the photographies, but in our real life, images are prevalent in today's life. Not only the personal digital photograph for entertainment, right? For instance, the surveillance and the security, you have all the factors which might be contribute to the degradation of image, how to get a better one. And also in the medical image, you also need how to boost the resolutions and reduce the noise so the doctor can better examine or diagnose your health based on these images, as well as so-called remote sensing. Also, scientific image. Today, this what I show you is one image from biological image. This is actually an image for a virus. So this image will help the biologist to develop better cures or drugs for this to handle these virus things. So what I'm trying to say is that images are universal. Digital photograph is one of them. Here I show you some how to use deep learning to solving this image processing problem, which actually can be also used to deal with other type of images, which actually has a wide range of applications in a wide range of domains. Okay, the three keywords I want to say is that for image restoration, deep learning cannot be used as a black box. Okay, secondly, integration of math and statistics and deep learning is the key. The third one, unsupervised or self-supervised learning is the future. Okay, maybe I have a few minutes to introduce this one. So, so basically, this talk is that I show you that how the machine learning, math, and statistics can be combined together to develop powerful solutions to industry applications. Okay, so this is actually one motivation that why we introduced the so-called math program in data science and machine learning at NUS. So it is a multidisciplinary graduate degree by course designed for the next generation of leaders in data science. So the talk I just give you one example, because image is one most important type of data. Okay, so I show you that how these things, a multidisciplinary approach, math, statistics, and machine learning can be put together to solve the problem. So this program is actually trying to achieve that, training the students with these three type of skills: statistics, math, and computer science, with a specialization in the machine learning. So this is a program structures. We have 4 core modules and 7 graduate certificate and 3 clusters. Okay, so 4 modules focus on the foundations, including deep learning, machine learning, big data, like optimization and cloud computing. All right, and you have that. Then you're gonna have these choose other modules so that you can specialize what you like deep learning for data science, big data for industry, data science in computer vision, data science in quantitative finance, or you just select which specialization you want to go. Okay, so hopefully this program structure can give you a solid foundation so that you can develop yourself in future and prepare yourself well as provide you your training on specialized skills. So it can help you get the job you want. This is admission criteria. We want a bachelor degree with a strong background on quantitative science, like math, applied math, or computer science, or statistics, or physics. All right. Then, of course, if you are not native English speaker, you have certain requirement on the language. Okay, and the full time will be 12 months, and it can extend it to the 24 months, and you have part-time, of course, to a double time. And this is the fee structures. The fee will be 48,000, and it's self-funded. Okay. Then the next intake is the next August, and the application start right now. So it starts from tomorrow all the way to the end of next January. Okay, any questions? Let's see, well. So I will answer the first one question that he said, can I solve the task of training data problem by getting a normal high resolutions followed by blurred by passing through to some kernels? Then I have one. Good, that's a very good question. Yes, you can. However, if you have tried it before, because then your trained network will be specifically optimized for that particular type of blur kernels. Okay, that is, suppose I synthesize an image using the high-resolution image and blur kernels. Then actually this kind of supervised learning is not adaptive in the sense that if the kernel changed, then your trained network will fail. So in other words, you have to train the network, one network for each kernel type. And in practice, your blur kernel is not like always the same, right? Of course, it's the same, then you don't have unsupervised case. But if you want a universal model, so that I don't care what blur kernel is, I always can process it, then usually you have to go to unsupervised. Because if you take a supervised way to do it, you actually can only process, your network only can process that type of kernel. Actually, that's specific of kernel. And if you use it to process the image which blurred by other kernels, the result is actually not good. Okay, that's my answer to the first question. My second one, okay, basically what contribute to the solution of, what contribute to the solution of the photo restoration? Actually, I not so understand this question well. You say, what plays rules so that you have a good solution of photo resolution, photo restoration? If that's the case, in older time, people try to assume certain prior knowledge on the image. That is, for instance, if you are taking a scan a document, you assume that it's text. Text, we know what's text, right? It's small lines, but small lines and usually is straight. That prior is used in like older time. People do that using manually design these kind of things. But today, machine learning is trying to automatically capture the prior of your image so that it can develop a better image from the poor one. What's the next one? Can network able to apply one photo with huge difference in contrast so that you can see the examples provided by? Yes, I think it's actually contrast enhancement is not a hard problem. It's essentially just try to how to better adjust the histogram of the brightness. You can. The answer will be positive. It's actually not very difficult task to do. So last one in photo, next one in photo restoration. Are there other aligned to chain besides using DNA? Can we use decision tree forest? Okay, I haven't seen any result using decision forest to do this problem. Why? Because in the image restoration, we are talking about a function that is a mapping from image to another image. So random forest or decision tree is good to make decision. As a result, it is suitable for the classification problem. That is, my input is image. My output is a label. 1, 2, 3, 4, 5. Like 1 is cat, 2 is dog, 3 is maybe mouse or something. But for the image processing, you don't have decision because you have to guess every value, the value of every pixel. So it will be overwhelming if you think about in terms of decision trees. So far, I don't see any work declare that they can using random forest to do this image restoration problem. Okay. Okay, is it possible to do incremental training from initial training data? The aim is to get good enough model plant data, but ongoing to keep feed smaller training them. Of course you can. However, for the image processing, that's a different story. So suppose you already have a large amount of training examples. You train a network with good result, right? Then you say, I have new data coming in. Then this new data, well, you have two possibilities. One is this data is actually very similar to the data you already collected before. Then there's no need for the training because you already trained that. Second one is the new data comes in, which is very different from the data you collected in the past. Then it is a bit dangerous to train the network with small amount of the current one so that it adjusts the old one. Why? Because you might introduce big bias, which is from the old training data. So I will say, if your new data comes in, I will, if I was assigned to such a job, I will probably pick up some data from the old time, which probably have high correlations with the current data coming in. Then I train the network. That is probably more safe. Otherwise, you might worry about the bias introduced by the old data set.